Right, we're going to learn about the structure of metals today. And you already know a lot of the properties of metals, such as the fact they conduct electricity, they conduct heat, they can be changed shape without breaking, so malleability, or they can fall into wire, ductility, and they have relatively high melting points and boiling points. I'm going to show you a lot of these. So we need to be able to explain them in terms of what particles are made up of and in terms of the forces. Now the book's a little bit simplistic with the particles, however the description it has is still correct for NCEA. I'm going to sort of tell you more what it is rather than what NCEA expects. So the basic structure of a metal, and this is like your iron, your aluminium, it's most of the elements on the periodic table. Alright, so for most of them, they all have the same general structure. And what you find is that they all have got only a few valence or outer electrons. Those electrons can be lost and put into a sea of valence electrons. And of course, if those electrons don't belong to a particular atom anymore, then those atoms have become cations or positive ions. So the particles are cations, positive ions, in a sea of valence electrons. Now, the reason we usually see is even though metals are a solid, the electrons are fluid, they're able to move around. Alright, so they're actually able to go from one part of the metal to the other. The metal stays as a solid, but the electrons are fluid, they're able to move. The reason that the whole thing is a solid is because the cations stay in quite a rigid structure. They're organised as a solid until, of course, you add enough heat that they melt. So this means that the relationship between these cations, even though they should repel each other, is actually quite strong. So there's got to be a pretty good force. The force is given the most obvious name. It's a metal, so we call them metallic bonds. But what a metallic bond really is, it's the relationship between the cation and the negative sea of valence electrons. It's what we call a radial force. It's a force that goes in every direction, and we're talking 3 dimensions, not just 2. So for every cation, it's got an attraction to every electron that's around it. And I can't show 3 dimensions on the board, but if you can imagine what I mean there. This means that that is quite a strong force. However, it's not strong enough to keep those electrons where they are because the electrons have got quite a lot of energy. So they can move around. That just means another electron will take its place and it's still got that attraction. And of course this electron here is also attracted to another cation. So this is what sort of creates your metallic bond, this radial attraction of each cation to all the electrons around, the valence electrons around it. And it's what gives our metal its property. The electrons are able to move from one place to another, so from A to B as it were, without breaking this bond. It stretches it, and then the bond gets made with a new cation, basically. And then a new electron is in there, so it's never actually broken. There's no real attraction between the cations, and that would make sense because they've got the same charge. If one cation gets too close to another, then it's going to repel that other cation as well. So if I was to make this vibrate quite a lot by giving it some energy, then it will get too close to other cations, and it will make them vibrate as well, get them too close to the other cations, and so you get a chain reaction. The increase in kinetic energy is actually the transfer of heat. So that's what we see for thermal conduction. We're going to have a look at some of these things in a moment, as I say. So we link everything back to the structure. Cations and a sea of valence electrons. The book says atoms and valence electrons. That's fine for NCEA, but of course that would mean that you must have a negatively charged object, which you don't. So your book's technically wrong, but it would be fine for an NCEA answer. Right, so let's go through a few of these things here. First one we'll look at electrical conductivity, just using the simple apparatus we used last time. So I've got a lamp set up and a broken circuit. So if the lamp goes on, we know it's conducting, and I can even do it through the bench. because the dent is made of an alloy called steel. Alright, got 4 metals here. I've got a piece of magnesium. So you can see that it's shiny, so we know that it's not covered by an oxide layer. And you can see it goes really, really brightly, even though the two leads are quite far apart. So it's telling us it's a really good conductor. If you remember in the last one, the ionic solution didn't conduct this well. It was at the same voltage, everything was the same equipment as last time, but it didn't conduct anywhere nearly that well. I still wouldn't want to be in a saltwater pool when a lightning storm was happening, but I'd almost certainly not want to be holding anything metal during a lightning storm either, because it's an even better conductor. Okay, so that's magnesium. Got a bit of copper here. Again, it's shiny, so we know that it's clean and it's not got oxide all over it. And again, a really good conductor. You see a bit of a trend here. I'm not sure what that one is. I'd say that's zinc actually. It has got a bit of an oxide layer, so it may not go quite so well, but let's have a look. It's pretty good, even with an oxide layer. And an iron nail. So we can see that some common metals are very, very, very good conductors. Why is this? Well, if I reproduce my diagram, I'm going to give it a bit of structure here. It's solid, so the particles must be organised. So I've got all the cations. In between those and all of these, we've got our sea of valence electrons. And again, C means that the electrons can move, thus move. They're able to go from one place to another. If I add a negative charge over here, so I've connected it to the negative terminal of my circuit, then if the circuit's complete, then it's going to do what to the particles in here? Well, it's going to attract the cations because they're the opposite charge, but actually the cations are in a nice rigid structure, so that would attract the whole item. It doesn't do that because the force isn't strong enough. The electrical force is not strong enough to actually attract the whole piece of iron or the whole piece of copper across. So instead, it's like a path of least resistance. It's attracting the cations, it's also repelling the electrons, but the electrons can move independently. So what happens is the electrons start moving from here this way to get as far away from the negative charge as they can. Now they can only do it if there's a positive terminal over this side as well, because they need somewhere to go to complete the circuit. Because it's a sea of valence electrons, they can move from one place to another. So we have those requirements for electrical conductor. We have charged particles, both the cations and the electrons. But we also have that other key criteria, that the particles are able to move. The cations can't, too much energy required, but the electrons can. We have an electrical conductor. Alright, so what about thermal conduction? I'm just going to do thermal conduction and melting bonding points together. So the first one I'm going to do is see what happens if I just heat a bit of iron. Just go blue flame for this. And I don't really see much. You can see it tarnishing. There's no way I'm going to touch that with my skin now. Okay? But it's just tarnishing. That means it's getting very hot very easily. Okay? So it can absorb heat energy very easily. I wouldn't even touch this end if I didn't have the tongs because it's going to be so hot. Alright? So it didn't melt. Even though I'm looking at a few hundred degrees, it didn't melt, and it sure as heck didn't boil. My zinc should be a similar sort of thing, I hope, if I heat just the end of it. Okay. Now this one's starting to melt, so some of them have got slightly lower melting boiling points. Whoops, that's done a little bit too well. And you see the structure changes if they melt. They go into little globules, as it were. Right? So it was obviously hot enough to melt that one, but not boil it. Okay, so if we think about the ionic solids, they've got lower melting and boiling points than those. And of course the last one, which I'm asking you to not look directly at, just look at it using your peripheral vision. The camera can look directly at it, right? Is magnesium. And rather than melting, it actually catches fire instead. Okay. Right. So it can't even get to the temperature that it needs to melt before it actually reacts instead. Now, why do these metals conduct? Why are their melting points high, but not nearly as high as the ionic substances?
What about copper?
Yeah, what about copper?
Copper, okay. Sorry, I know you're a little on the boring side, so because it doesn't even change colour or anything. Leave that one out. But you can sort of see the heat wave move if you look closely enough at it. It sort of moves across. But that's all you'll see. So it's a little bit on the rain side. Okay, and it's starting to tarnish as well. So that's the reaction with air. It's a slow reaction, a much slower reaction than the magnesium one, which slowly will get the fire. Okay, so the reason that it has got thermal conductivity, so you can see that it's starting to tarnish as it moves across, even though that bit wasn't in the flame. The reason is due to the same structure, but rather than the electrons being moved now, it's because we start to vibrate, and I'll zoom in on this one, when you start to vibrate the cations. And if we start to vibrate even one cation, then it ends up getting too close to another one. And because they both have the same charge, they repel. So if this one starts vibrating, then it makes this one vibrate a little bit, makes this one vibrate a little bit, and by now maybe the vibration is only a little bit there. The more I heat this one, the more this one vibrates, the more this one does, and so on. And that's your thermal conduction. That vibration is heat energy, and increases temperature. Okay? Average kinetic energy goes up, so temperature goes up. The reason that it's got a relatively high melting and boiling point, yep, I know our zinc started to melt there, but our others didn't, is again due to the forces. Metallic forces, or metallic bonds, say, even though they're radial and relatively weak, there's so many of them, there's so many forces that actually it's quite strong. So you've got quite strong forces there. And it's due to the number of them, not necessarily the strength of them, right? Each cation has got a strong, it's got many relationships. So lots of electrons, valence electrons linked to it, and let's see. The last thing we're going to look at, just hoping this is cooled down enough, and I'll just show you another cold water to make sure, is the malleability. We're going to be cold enough now. And so I'm just going to use zinc, but I could use any of these parts of the iron nails because I'm not strong enough. And malleability just means I can change the shape without actually breaking it. That's all it means. Ductility means drawing it into wire, and I mean these copper wires, so inside the plastic. So we know from experience that can be done as well. So what that's saying is I can put the bonds and the particles under pressure, so I can apply a force to them and change something about it without actually breaking the bonds. So how can that be the case? If these bonds are strong enough to give them relatively high melting boiling points, how come I can change the shape without actually breaking any chemical bonds in there, without breaking the substance? Well, again, that's to do with this radial type of force that's in the metallic bonds. I can break one or two of these bonds, and then they'll immediately reform once there's a change in shape. So I can actually I can break this to allow me to move that cation, or a series of cations, and then it'll reform straight away. It's still got lots and lots of other forces in place, but as well as that, these bonds can stretch and compress without breaking. So what I'm trying to do, if you imagine that these are the two cations, I'm wanting to move this cation from here to maybe here. To do so, I have to break the bonds in between them just for a while, but then they can immediately create new metallic bonds with the electrons in between them here. So it doesn't actually have to break the structure, the overall structure. It just breaks a couple of the bonds within the structure for just a moment. Now, if I was to heat this and then cool it really fast, then it creates a slightly different crystal structure, and then it will snap. And there's certain types of steel that do that. They're a lot harder, so they're a lot stronger, but they actually shatter. Right? And they're going more like a different type of structure, less metallic bonding, it's more like your covalent networks, to be honest. It's a lot more rigid. So it's stronger steel, but it's not so malleable. So basically what we're looking at is the fact that these bonds, you can break a couple of them without breaking the entire structure. If you break a bond in an ionic compound, you shatter the compound. You've got to break a lot of them at once. You can break just a few bonds here, change its shape, and as soon as I stop applying force, those bonds reform just in a different position. Okay. So these are the big four that you need to be able to explain in terms of structure and bonding for your assessment, but also to actually have a good understanding of what metals are. The last thing I want to show you very quickly is this. I've got two metals bolted together, just to show you that not all metals are created equal. If I heat it, they're both going to get the same amount of heat energy, but we should get an interesting observation. Sorry? I am not 100% sure, to be honest. No, I'm not sure. So tarnished that I can't tell anymore. Okay? But what we should see, if I heat two of them evenly, a little bit of time, it doesn't want to work in, so I'll do a smaller one. Not invented too much up notice, it's going to be hard to do it otherwise. Yeah, it's starting to be a bit slow. I'm going to show you the smaller one. Okay, same idea here. This will go a lot quicker. Okay, we start to see that that it starts to bend. Okay, so what that is showing is that one metal expands a lot more easily than the other. So one is actually vibrating, the particles vibrate a lot quicker. So this tells us that different metals can have slightly different properties. Just like we saw for different melting points, we can also have differences in things like expansion and contraction. And that's normally to do with the mass of the cations and the density of the actual metal itself. Okay. Same thing with conduction. If we had accurate enough equipment, we could look at we could do relative conductivity, so electrical conductivity, and again that's due to how many electrons are in the sea of electrons and that sort of thing. Alright, so they're not all created equal, but there are general trends. They all conduct electricity, they all conduct heat, they're all malleable or ductile in solid, and they all have relatively high melting boiling points, with one exception, and that's mercury. Okay, it's a special case. It's very unexpected.